So the next part of this workshop here is the last set of talks. We're trying something a little bit different that's not generally done at NASA meetings, but is done at a lot of other things, especially here in Silicon Valley. So please bear with me. It's a little bit of an experiment. Let's see if we can twist your minds a little bit. We're going to do a series of lightning talks. There are no questions. This is really meant to allow people just to say an idea or two, for you to absorb that, and of course follow up in discussions the rest of the day. We have, I think, 13 speakers. They each have 2 minutes each. As I said, no questions, but take notes. And if you see somebody say something of interest or hear something of interest, note who they are. You can go follow up with them afterwards. We're going to run through this by alphabetical order by first name. And so the first one up is Ariel.
Thank you. Good morning. My name is Ariel Deutsch, and I'm a graduate student at Brown University. I study planetary science, so I'm not here to pitch to you a new piece of technology, but what I can do is propose to you a scientifically interesting place that we would like to explore that really requires your innovation to help us get us there, and that's the poles of Mercury. Most of my research focuses on these permanently shadowed regions at the North Polar region of Mercury that hosts radar-bright materials indicative of water ice. And these water ice deposits are really, really pure. They're 95% pure water ice, and they're also very thick. They're on the order of meters thick deposits, and they're just sitting at the poles of Mercury. Many of the deposits, such as the example on the right, also are insulated by thin layer of organic materials, and these have been observed both in images as well as in the reflectance data. And so this offers the opportunity to explore some of the most primitive materials in the solar system, while also answering questions about where our water on our own planet may have come from. And so on Mercury, if you land in any of these pink regions shown here, you're going to land on some of these most massive examples of water ice in the inner solar system. And so I can imagine some sort of fleet where you could explore these water ice deposits while also harvesting them for ISRU. But as a scientist, we can identify these questions that we answer and instruments that could help us answer these questions, but it's really up to you as engineers to help make our dreams our reality. And so if you're interested in chatting about this, please come and find me, and thank you for listening.
Hi, my name is Darlene Lim. I'm based here at NASA Ames, and the person who is literally beaming with joy and wonder on the slide behind me is my dear friend Zena Cardman. Zena and I have worked together for over a decade on a number of different NASA analogs, and she was just chosen to be a NASA astronaut candidate. She's 29 years old, and wait for it, she is an aquatic scientist, not some sort of flight engineer. And so she's my slide because when I think of a science mission of the future, I imagine Zena out there in deep space on Mars. I imagine a mission architecture that will enable her to basically optimize scientific productivity and to promote discovery for the bevy of scientists that will be here on Earth, people like me who will be stuck here, very old, but very, very excited about what's happening out there. So we have worked together on doing real, non-simulated analog science under simulated deep space and Mars mission conditions. We use the science, the fundamentals of science, to drive out the demons of operational EVA complexity so that we can generate EVAs designed to enable scientific exploration with humans and robotic elements working together. So to get to the punchline very quickly, there are kind of two elements that we found at a very high level that bog us down. Number one, for the astronauts, it's the time and the current shortage of it in our experimental EVA timelines. And number two, for the Science and Mission Support Center, it's the seeming lack of scientific and operational situational awareness that's provided to them from the field or eventually from deep space or Mars. So in both cases, there are significant trickle-down effects to these limitations that effectively affect the quality of scientific return. And the honest truth of our tests is that we are limited by the capabilities that we have at hand, by the technology that we can absorb right now. And those limitations bear down on us, but whether it's how much we can afford to actually implement or what's actually available to us at this point in time. So we would like to, we've wondered lots of different things, like can automated speech recognition, natural language learning integrated together actually with geolocated elements, can that actually get us to a situation where Xena doesn't have to say or touch or do as much as she does have to right now in order to manage her environment? Because the more she does of that, the less she can do of this kind of smiling and beaming and being her very incredible scientific self. So that's it for me.
I'm Harry Partridge. I'm the chief technologist at Ames, and I wrote out some things to say, but a lot of it's already been said. I think that autonomy is crucial for NASA, both from a cost, a reliability, and a safety issue. It also dramatically will expand, I think, the range of missions that we can do. We do need to leverage and spin in what industry is doing. And leverage that investments. I would like to say about the cars. They talked about the autonomous cars. They talked about safety. When I retire, I'm planning to move to Colorado, where we're already planning on autonomous cars for where we're willing to buy a house. So I expect to be able to move that way. Also point out that he talked about safety and reliability, but road usage, 10% of autonomous cars will significantly improve the usage of the facility, so you don't need to build as many roads. So it has more effects than just on the autonomous vehicle itself. If you can start communicating, you can then do autonomous swarms of things. In cars, you won't do that, but in NASA, we will. Like to point out from a technology point of view, the computing requirements necessary to do autonomy, they're significant. You really need the high performance space computing if we're going to insert this in NASA missions. And the final thing is that assured autonomy is critical for NASA missions. We don't have a lot of vehicles, so it's not a statistical. We need to be able to understand what's happening, why it's happening, and where do we interface with that. Thank you very much.
Good morning. My name is Issa Nesnas, and I work in robotics and autonomy at JPL. So I often enjoy talking to the skeptics about autonomy, and the question always comes up, why do we need autonomy? So I'm going to give you a perspective on autonomy and why we need autonomy for the future. If we take a historical perspective, past, present, and future, and we look a lot of the exploration that we've done in the past, relied a lot on spacecrafts, flybys, and orbiters, and we discovered our solar system that way. And at present, we've seen more sophisticated type of spacecraft, landers, and a lot of rover over the past 2 decades. And one could argue that in the future, we're going to see quite a bit of combination of robotics and autonomy to explore future spacecraft. But why? Let's take a look at the past. In the past, I would argue that a lot of the challenges, and it's quite severe challenges, but they were dealing with understanding orbital dynamics and understanding the space environment. So we had an ability to deal with uncertainties that one could argue that were smaller than what we have to deal with in the future, especially when we get to the surfaces of these unknown bodies. For these, we had good dynamical models, orbital dynamics models for spacecraft that we relied on and gave us an ability to predict. In the future, if we start going to places such as Titan and other environments, our ability to predict how we're going to move and interact in the environment is going to be much more limited. We've also seen a significant advance in computing and sensing, and we're going to be dealing with far more richer data on board these explorers than we've ever seen in the past. And as to kind of conclude, the forms of explorers transitions from purely orbiters and flyby type of missions to more complex forms that we're likely to see multiple spacecrafts, like to see balloon type of missions, landers, orbiters, and subsurface explorers. So I would collect it. In the past, we had an ability where we had higher predictability, and that's why we could sequence things over a larger periods of time. In the future, what we really need is greater flexibility, and that's where the autonomy things come into play, which is captured in these things of the different types of robotic capabilities, as well as the reasoning and cognition capabilities that we need. And the probabilistic reasoning that was mentioned earlier is going to be a very critical capability. But ultimately, to build autonomous spacecraft, we really have to design for autonomy. It's not just adding autonomy as an add-on, but actually designing from the ground up for autonomy, and covers a number of areas. You can see here 2 areas is the function level autonomy, the functions that we need, as well as the systems. And that will enable us to have greater access, more versatile operation, and richer exploration in the future.
Hi, I'm JP. I'm a roboticist at JPL working on multi-agent robotic systems, and I'm here to stimulate a discussion about what can we do if we send more than just one robot, maybe 2, maybe 5, maybe 50, maybe 100. And I really think that multi-robot coordination could enable some more improved and new capabilities that we haven't seen yet. So some of these that I've been thinking about are, for example, distributed search. Obviously, if you have more robots, you can do more things in parallel, right? So you ought to be able to do your tasks faster if they're parallelizable. Then there's maybe distributed sample gathering, and this is really more of a coordinated problem where you have multiple assets and maybe you have a heterogeneous system. So you don't necessarily need to build all your robots to be exactly the same and send 50 copies of one. Can maybe think about sending one that has more of the science instruments, and then others that just go out and they gather whatever is interesting and they bring it back for processing, right? And then also you might be able to do some coordinated behavior like distributed science samples. So now all of a sudden, before you had to go and survey several different sites, now you go send them out and they do it at the same time, and you get data in multiple places at the same time. So I have kind of a diagram of a sample mission that incorporates all of that, but I just wanted to add that there's even more coordinated behaviors that we kind of think about, including formation transit, there's cooperative manipulation, there's self-assembly, multi-objective tracking, and I'm certain people in this room can even think of more types of coordinations that we could possibly leverage on future missions.
Hello, I'm Jeff Sheehy. I'm the Chief Engineer of Space Technology Mission Directorate. Our job is to develop and demonstrate the technologies that Science Mission Directorate and Human Exploration Operations Mission Directorate can use in their missions. So I was on my way to San Jose, and Terry said, "Hey, would you like to do a lightning talk?" And that was a tough task for me, but 2 minutes. So I pulled this picture off the cover of the Science Definition Team report for the Europa Lander mission, because this is the kind of mission that excites me. And there's a quote that was in the that I pulled out of the report that says the sampling system needs to be capable of conducting a sampling cycle in a fully autonomous fashion with no input from ground operators. So I don't know what level of autonomy this is, and for example, in Terry's taxonomy, but I think it's beyond anything that we've done so far on a NASA mission. And we want to be able to get to missions like this. This is something that's being studied in the NASA Innovative Advanced Concepts Program. It's one of the programs in STMD, looks at conceptual studies of kind of far out there sorts of missions. This is a Titan submarine, and I'll go back. And in any case, this would have to be a fully autonomous mission. You'd basically dunk it in the methane lake on Titan and say, good luck, report back in a month. And so, this shows you a little bit about the levels of autonomy that I think are very interesting, the missions that excite me. And what I'm looking for out of this conference or this workshop is some notion of what can we work on now? And there's a sense in which it seems like an enormous task that trillion-dollar almost companies have to undertake and spend years trying to develop and implement. But what can we work on now to enable these kinds of missions?
Hi, so my name is Jeremy Frank, and Terry actually talked about a lot of the things that I'm going to talk about here. So what I'm going to do really is sort of extemporaneize about automated planning technology, and in particular what in the artificial intelligence community is called model-based planning. So model-based planning is not just a planning system that's built and dedicated to solving a single problem. It's meant to be a general purpose planning system into which you feed a description of what kind of planning problem you want to solve. And the intent is that then it can produce plans for not just one, but many different types of application. And so if you look at the elementary operations that planning systems do here on the one hand, and if you look at the kinds of constraints that you need planning systems to solve, the intent is that you build a declarative description of what these constraints are, and you feed it to this piece of software. So the first thing the software does is reads a description of, if you like, the physics of your world. So the advantages of systems like model-based planning systems are that they're very general purpose. They can be used for a lot of different applications. You can make arguments about how easy they are to mature for single applications, because you can build a sort of simple description of your problem and you can refine it over time and make it a lot better. The disadvantage, as people like Butler was saying, is that you have testing problems with systems like this. They're quite complex. The computational resources required to solve these problems are in general very high. But this class of automated model-based planning has, in my opinion, a variety of benefits, not the least of which is that ultimately we'd like to be able to learn what those models are, not necessarily onboard your spacecraft on the fly in the near term, but maybe in the far term you can do that. So quite above and beyond model-based planning as one of the kinds of foundational technologies that we want in order to accomplish these missions, what are some of the opportunities and the challenges? So we've alluded to opportunities like increased science return, increased flexibility, like Issa in his very excellent overview gave. We have reduced dependence on communications, and there are some interesting knock-on size, weight, and power reductions that may be possible from that. There are a variety of challenges. Existing algorithms are very complex. Can we simplify them? How do we fit them within our CPU boxes, and so on and so forth? There are a variety of technologies available both within NASA and within academia that I can talk about later with those who are interested. Thank you.
Good morning. My name is Kai Goebel. I'm the Tech Area Lead for Discovery and Systems Health here at NASA Ames. I'm here to advocate for a capability that I call a design for resilience. If we are buying in that autonomy is needed, and that is not a bad assertion to make if you're at a workshop for autonomy, then you have to ask yourself, how do you build these things so that they're maximally supporting your mission? And I think we really need to have a new philosophy that enables that, both with regards to hardware as well as software. Hardware, so that you have the kind of functional redundancies as well as flexibilities to reconfigure on the fly. Software to support decision-making kind of abilities as well as control reconfiguration. And the methodology needed to carry that out really involves design optimization principles. They involve principles for life cycle assessment and all kinds of what-if analysis, and put that all together to come up with the optimal design for your mission. Thank you.
Autonomy in space is right now hamstrung by the hardware we're permitted to send to run it. It lags state of the art by about a decade. Neuromorphic computing is a different style of computing that promises to be fast, low power, and robust in these harsh environments, mainly because it, one, does not necessarily do precise math in the same way that a standard computer would, and also because it doesn't necessarily rely on the electronic components in the computer being in a stable state, so it is robust to bit errors. However, these kinds of computers are very difficult to program. Hypervector, high-dimensional computing, hypervector computing, which was developed by Pentti Kanavera, first at Stanford and then here at Ames and now at Berkeley, is the programming language we need to develop these computers, or to program these computers. And one of the benefits is it can do, for example, analogy-based reasoning in constant or linear time, and that is something that could let us have robots that build models and test them, which means we could have machines that are doing science in space without our help. So I would suggest that we should start looking at this new style of computing and developing machines that use and learn with this style of highly distributed and robust computing. Thank you.
Hi, my name is Neerav Shah. I'm at NASA Goddard Space Flight Center. I do advanced guidance, navigation, and control. So I've been focused on precision formation flying for part of my career, and about 15 or 20 years ago, there are a lot of ideas out there about PFF, starting with the Black Hole Imager, the Maxim mission, New Worlds Observer, and those are up there in the top right as probe and decadal class missions. Now they're super complicated and fraught with a lot of risk. So I've been, over the past couple of years, been doing some R&D on trying to reduce that risk. Now, how can we do that, right? Small sats have been great. You can do a lot of things for low cost. And so we proposed some missions, and we're flying several CubeSat class missions. And there's a path towards getting up to those decadal class missions through what I'm calling these science pathfinders. Now, all of these missions, they require advances in guidance, navigation, and control, onboard autonomy. I'm not sure how the technology today can be folded into that, but I strongly believe that if there's more autonomy, these things become a lot easier. Thank you.
Did you lose alphabetical? Can't spell. Peter comes before Randy. I don't have a chart, so. My name's Randy Lillard from Johnson Space Center. I didn't give a chart because what I know about autonomy wouldn't fill up a chart. So, what I want to talk to you about is what HEO needs and where I think maybe you can help us and industry can help us. So, if you're not familiar with what HEO is doing right now, we're looking at what we're going to do beyond space station. You've heard the cislunar gateway, and this. So our next. After the EM1 and 2 Orion missions, we're looking at what Orion does after that. The current plans are to send a habitat and the power prop bus around cislunar space. When we go there, our crew will only be there 10% of the time throughout the year, so maybe 30 days out of a year we'll have crew there. So we'll have a vehicle there untended. A couple things we want to make sure we understand about autonomy is how do we manage that vehicle with nobody there? Right now our paradigm is the crew hit a lot of buttons, and the ground tells the vehicle a lot what to do. With a reduced pipe to that vehicle, because we'll be using DSN, and with no crew there, we need to get how autonomous does that vehicle need to be. The other piece of that is we want to make sure that that vehicle can do science and do things while it's there with no people. Right now on station, again, we're pretty heavily dependent on our crew to do our science. So we need to understand how we can do that autonomy and how to run that vehicle while crew is there, without crew there. What we're currently doing is going through our ConOps and our operations people. You can imagine we have a long history of how to operate a vehicle, and they like to do it a certain way. So we're looking at how they're doing it now and pushing them on where do you need the in-depth interaction, where do you need the in-depth oversight, and where don't you need it? And then how can we have the autonomy help you make decisions or make decisions for you depending on that level of the vehicle. What I hope to come here for was to really learn what SMD is doing so we can look for some overlap areas where SMD could help HEO. Because I'm thinking even though the science might not be the same, the vehicle still has thermal issues, still has power, still has all the things you need to manage on its own, just like our vehicles will have in HEO. And something else we're looking at that I was glad to see our friend from Nissan here was what can we spin in from outside? I feel like we have a little bit of money in STMD. It's great. We have a little bit of money in HEO to do these kind of things, but there's a lot of money being spent outside. And where can we look outside our gates to find solutions to come in and solve our problems? So I'll leave you with that.
honestly didn't know I have time, but let me just share. I think there's a number of really big challenges we have to address as a community, and we have to come to grips what exactly we mean by autonomy, where these common intersection points are between the mission directorates, and really coming in terms where the priorities are going to lie so that we could enable these missions of SMD and beyond. A lot of this is going to be technology challenges. There's going to be a lot of cultural challenges, but we've done this before. I've witnessed an increase in automation in our control centers at Goddard from the mid-'80s till now using some just simple technologies, but it's one of these things we need to start engaging the community at a broader level, bringing in the science community, bringing in the project managers, getting them engaged with it so they understand what that risk level is and what they're buying into. You know, we all have reservations about accepting this technology. I have reservations about getting an autonomous car, and at times, and you know, would I put my 10-year-old daughter in that to send her to soccer practice and things like that? I'm willing to say yes, but when you talk to a scientist and ask them if they want to put a payload that they're resting the rest of their mission on, they're not going to make that decision until they have the transparency, understand what that risk level is and what it's really going to buy them and whether it's going to be affordable. So it's those type of things we're going to have to work together on so we could understand if and how autonomy will play a role and at what level we're going to accept that. Thank you.
How do you, oh, okay. So, I'm the last one, so I can continue to talk, right? So we start with a card, right? So it's you know, has a lot of sensor in there, and then we are moving into the space. The IoT in space, Internet of Things in space is, in my opinion, in my mind, is all the small sat, all the satellite constellation. How do we point to the right direction, get correct information? That requires a lot of intelligence built into our spacecraft to coordinate that kind of observation. We know how to build that kind of architecture on the ground. In our data system, we had data-centric architecture, and with all the decisions made on the edges, all the different computer on the edges, that kind of architecture is becoming available during the EM rolled out event. HP actually announced the machine, memory-centric machine, has memory in the middle and all the computation around at the edges. Okay, that machine has the architecture in the middle, lower middle, has 4 terabytes of memory right on that board, right on that system. So going to space with that kind of a supercomputer will kind of can resolve a lot of data mining, artificial intelligence, autonomy type of application. Now finally, moving to space, we always talked about radiation hardening computing system. In this case, we are flying 2 Pleiades modes to ISS. It's going to be in space. We are going to test the radiation environment and to see the memory fault behavior and whether or not it will impact our calculation. And we can actually slow down. Our computer has built-in self-healing mechanism, so we may be able to use just regular computer in space. Thank you.
Great. Well, thank you very much, everybody who agreed to give a lightning talk. I hope you all got some ideas, or maybe now you have some additional questions you want to follow up and ask everybody.